So now good?
Are we recording it? Yes.
Yeah. Okay. Yeah. So thank you everyone for coming, and thank you to the organizers for putting this all together and for the invitation to speak here. So I'm going to tell you about this topic that I've been interested in for the last couple of years or so that I call combinatorial billiards. So the idea is there's this area called mathematical billiards that tries to study the dynamics of a beam of light that kind of bounces around, maybe in some crazy way, like what's shown here. And then there's a field called dynamical algebraic combinatorics that tries to study dynamical systems defined on objects of interest in algebraic combinatorics. And so combinatorial billiards is going to try to merge these two areas by considering billiard systems that are, in some sense, very rigid and constrained and maybe discretized so that we can think about them combinatorially or algebraically. And the questions that we ask about these combinatorial billiard systems will be different from what we would ask about mathematical billiards. So maybe in mathematical billiards, you might ask things like, do you have any periodic orbits, or do you get chaotic behavior? Whereas in combinatorial billiards, we're not going to have chaotic behavior. And we might ask very precise questions like, what are the exact lengths of the periodic orbits? So the basic setup is we're going to take the Coxeter arrangement of a Coxeter group W. If you don't know what this means, that's fine. I'm going to work with a specific Coxeter group called the affine symmetric group, which I'll define in a few minutes. But for now, you can just think this is some group, and it gives rise to some hyperplane arrangement. And we're going to shine a beam of light in some direction. And whenever the beam of light hits a hyperplane in this arrangement, it can change its direction according to some rule. And we're sort of free to choose the rule to be whatever we want it to be to get whatever phenomena we want to consider. So maybe with one set of rules, we have some interesting phenomena. Maybe with a different set of rules, we get another set of phenomena. And in each case, we're going to try to discretize the beam of light by thinking about it as moving along in sort of a step-by-step procedure. Okay, so here's a picture that is from a paper that is not the paper that I'm talking about here, but I think it illustrates what I'm saying. So this is the Coxeter arrangement of the affine symmetric group S3 tilde. And so it's like the equilateral triangular grid. And here I have this shaded convex set down here. And starting at this point, I decided to shine a beam of light down in this direction here. And the rule in this setting is that the beam of light is not allowed to move strictly away from this shaded convex set. So basically it moves down here, but then when it gets to this hyperplane, it can't keep going, because if it did, it would be moving strictly further away from this shaded set. So at this point, it has to reflect. And so it does this so that the angle of incidence equals the angle of reflection, like a usual beam of light would do. And so then it reflects and it moves over to here until it gets to this hyperplane, but then it can't keep going because it would be moving strictly away from this shaded set. So it reflects again, and then it ends up in this shaded set, and it starts bouncing around in the way that a beam of light would bounce around. But what I want to focus on are these arrows, which are representing how we're discretizing the beam of light. So basically, you can think that the beam of light starts in this triangle, and then it moves to this triangle, and then it moves to this triangle, and then this triangle. And when it reflects, it stays in this triangle for a second, and then it moves to this triangle, and then this triangle, and this triangle, and so on. So really, you could think about the trajectory of the beam of light as just a sequence of triangles. And that's how we could think about it combinatorially. It's just a sequence of triangles. Okay, so this is another picture from the same paper that I'm not talking about, but it took me a long time to make this, so I wanted to show it off. Also, Grant Barkley helped make this. So this is a Coxeter group where the Coxeter arrangement naturally lives in this hyperbolic space. So it's in the Poincare disk model. Again, we have some shaded set, and we have this beam of light that's bouncing around in this hyperbolic space, and we can discretize it with these arrows. Okay, so there are a lot of perspectives you can have in combinatorial billiards. So one of them is coming from dynamical algebraic combinatorics. Specifically, there's this operator called promotion, which was introduced by Schutzenberger in order to understand the Robinson-Shenstedt correspondence. But now promotion appears in a bunch of different places throughout algebraic combinatorics. And in this paper, which is joint with Grant Barkley and Elliot Hodges and Noah Kravitz and Mitchell Lee, we realized that you could actually think of promotion as a combinatorial billiard system. There's a specific way that you can actually think of it that way. And so then that got us interested in thinking about more general combinatorial billiard systems like the one that I'm showing here. And we were trying to classify Coxeter groups according to the behaviors of certain billiard systems living inside of them. I also have this paper with Pakawuchi Radulok where we have this connection with playbit graphs. So playbit graphs are these objects that were introduced by Alex Postnikov to understand the totally non-negative Grassmannian. Basically, it's a planar graph embedded in a disk where each vertex is either black or white. And if you have a playback graph, you can define these strands that kind of walk along the graph according to some rules called the rules of the road. And in some cases, you can dualize a playback graph to get a combinatorial billiard system. So that's sort of what I'm trying to illustrate here, where I've dualized this playback graph to get this combinatorial billiard system in this hyperbolic space. Now, in this paper, we were just focused on these systems in triangular grid polygons like this. And we had some number of different trajectories, which in this picture are in different colors. And we were trying to relate the number of different trajectories to the area of the polygon. So we get some kind of inequalities that have sort of an extremal feel to them. There's also this thing called refraction billiards. So this is a topic that people have studied over the last decade or so in dynamics. And the idea is that a beam of light can bend, or in other words, refract when it passes through a hyperplane. And so I have this paper with Ashley Adams and Jessica Stryker, where we give a combinatorial way of thinking about these refraction billiard systems. And we end up getting some interesting combinatorial dynamical systems, and we get things like the cyclic sieving phenomenon showing up. And this is a picture that I took of my collaborators taking a picture of a wall. So actually, after I gave a talk about this topic back in April, and Jessica and Ashley were in the audience, and then they liked this picture of the wall. So then they started sending me other pictures of them taking pictures of walls. So I didn't take this picture, but this is just them again with a wall. And then here again with a wall. And then actually Ashley sent me this picture. This is me, and then Jessica's there in the background, and we're also staring at a wall. I think this wasn't intentional, but it's also sort of in the same theme. This is at FIPSAC, and we were doing karaoke, and we had to project it against the wall. So you can see we're singing What Does the Fox Say there. Yeah, so anyway. So that's refraction billiards. There's also a topological perspective. So I have this ongoing project with Derek Liu, who was one of my students this past summer at the Duluth REU program. And basically the idea is that you can define certain combinatorial billiard systems in a torus. I'll say more about this later in the talk. But then you get these closed billiard trajectories that form these closed loops in the torus. And these closed loops have homology. And so you can ask, like, what is the homology? Like, are they contractible, for example? And so that's the subject of this work, which is still in progress. Okay, and then finally, there's probability. And this is what I'm actually going to be talking about today. And so this is me. And yeah, so it's based on this paper, Random Combinatorial Billiards in Stone Exclusion Processes. And yeah, so now I'm going to actually start defining things and going through this more methodically. Okay. So for me in this talk, the space where my billiard systems will live is this space V. It's the set of points in Rn whose coordinates sum up to 0. So this is just some n-1 dimensional Euclidean space. So if n is 3, I just get a 2-dimensional space like this. And for any distinct integers I and j between 1 and n, and any integer k, I can define this hyperplane inside of V, which is just the set of points in V such that the ith coordinate minus the jth coordinate equals k. So if I take the set of these hyperplanes with k equals 0, then this is what's called the finite braid arrangement, and I'll denote that by Hn. Okay. So in this picture for n equals 3, the finite braid arrangement is just these 3 thick black lines. And then if I take these hyperplanes, all of these hyperplanes that I've defined for all values of k, then that forms the affine braid arrangement, which I'll denote by Hn tilde. And so in this picture, that's just all of these infinitely many lines in this grid that I'm representing here. Okay. So the affine symmetric group, which I'll denote by Sn tilde, is the group generated by the reflections through the hyperplanes in the affine braid arrangement. So if you imagine taking one of these lines in this picture and reflecting through that line, that's some affine transformation of this space. And then if you take the group generated by all of these infinitely many affine reflections, that's going to be some infinite group. And that's the affine symmetric group, Sn tilde. And I should say this is an example of something called an affine Weil group. So some of the theorems and some of the definitions that I'll state in this talk do generalize to other affine Weil groups, but just for the sake of making things very explicit and concrete in this talk, I'm only going to focus on the affine symmetric group. And then there's also the symmetric group, which we could think of as just the group of permutations of the numbers from 1 to n. And I do want to think about it that way later in the talk. But you can also think about this geometrically as the group generated by the reflections through the hyperplanes in the finite braid arrangement. So like in this picture, if you look at the reflections through these three thick black lines, they generate some group of order 6, and that's isomorphic to the group of permutations of the numbers 1, 2, and 3. Okay. So if I take my space V and I throw away the hyperplanes in the finite braid arrangement, then the connected components of what I have left are called chambers. So in this picture for n equals 3, there are 6 chambers, right? So they're like these cones. One of them I've shaded in blue, and then there are these others that are not in blue. And if I take V and I throw away all of the hyperplanes in the affine braid arrangement, then the connected components of what I have left are called alcoves. So in this picture, the alcoves are these little unit triangles. Okay, so from now on, I'll say alcove instead of triangle. But in general, these alcoves are going to be n-1 dimensional simplices that are congruent to each other. Okay, now I'm going to fix a specific chamber called the fundamental chamber, and I'll denote that by C. I've written it here with coordinates. You don't really need to worry about the coordinates. Just think, okay, we fixed some special chamber, and we're calling it the fundamental chamber. And that's, in this picture, what I've shaded here in blue. And then there's also a special alcove called the fundamental alcove. Again, I've written it here with coordinates. You don't need to worry about the coordinates. But basically, this is just, well, you can think about it as the unique alcove in the fundamental chamber that touches the origin. So in this picture, it's this little A here. Okay. And there's a bijection from the symmetric group Sn to the set of chambers. Basically, it's because I defined the symmetric group geometrically as acting on the space V, right? It's generated by these reflections. And if you just apply that action to the fundamental chamber, then this ends up giving you this bijection. Or another way of saying this is a free and transitive action of the symmetric group on the set of chambers. So here there are 6 chambers, and that corresponds to the fact that there are 6 permutations of size 3. Okay. So I want to define a random walk that was introduced by Thomas Lamb about 10 or so years ago. We're going to start at the fundamental alcove A, and at each point in time, we're going to pick an adjacent alcove, and we're going to try to move into that adjacent alcove. And we choose it uniformly at random among the adjacent alcoves. However, we're not allowed to pass through a hyperplane in the affine braid arrangement if we've already crossed through that hyperplane. So if we're trying to cross through a hyperplane that we've already crossed through, then instead we just stay still, we just don't move. Okay, so let me show you an example. So this is actually a little AI-generated picture of me with a fish. I basically just needed some way of marking where we are in the random walk, and I kind of like this picture. I think the fish is kind of cute. Some people have said the fish is kind of creepy, but I like it. So anyway, we're going to start at the fundamental alcove here, and we're going to pick an adjacent alcove uniformly at random. So let's say I pick this one here. So I'm going to walk into that adjacent alcove, and I'll color this line pink to represent that we've crossed through that line. Okay, so now, again, I choose an adjacent alcove uniformly at random. Maybe I pick this one here. So I'll walk there, and I'll color this line pink. Now, again, I choose an adjacent alcove. Maybe I pick this one. But if I pick this one, I'm not allowed to move there because I can't go back through the pink line. So in this case, I just stay still. Okay, but now, again, I choose an adjacent alcove. Maybe I pick this one here, so I walk there. Now maybe I pick this one. Now maybe I pick this one. Now maybe I pick this one here, but I'm not allowed to move there because I can't go through a pink line. So I stay still. But now maybe I pick this one here, and then maybe this one here, and maybe this one here. So you can see I'm sort of wiggling along through this random walk, going off to infinity in some direction. Okay. Okay, so this is Lamb's reduced random walk. There's also a variant of this called the affine Grassmannian reduced random walk. You can think the words affine Grassmannian basically just mean fundamental chamber in this talk. So the point of this is it's the same rules as on the previous slide, except we're not allowed to leave the fundamental chamber. So another way of saying this is that you imagine the hyperplanes in the finite braid arrangement start off being pink. Okay, so here's a picture, again, me with the fish, and these thick black lines start off being pink. And I'm going to do the same thing as before, where at each step I just choose an adjacent alcove and try to move there, except I can't go through a pink line. So I'm going to end up walking along something like this, okay? Going off to infinity. Okay, so what Lamb realized is that you can project from the affine Grassmannian reduced random walk to a finite state Markov chain on the symmetric group called the multi-species totally asymmetric simple exclusion process, or multi-species TASEP, on a cycle. So this is some process that people have studied for a long time. And let me explain how this works for n equals 3 with this picture. So you can imagine you have this two-dimensional space V, right? So I'm only showing a piece of it here, but you can imagine you have the entire two-dimensional space V. And over here I have this little hexagon, which is basically like a copy of the symmetric group S3. So I have this hexagon with 6 little alcoves in it, and the alcoves are labeled in a natural way by the permutations of size 3. And so over here, I can tile my space V with these hexagons. So I just have this tiling, like here's a hexagon, here's a hexagon. And now there's a natural map that goes from the space V to this hexagon that just sends each alcove over here to the alcove of the same color in the hexagon. So all of these yellow triangles get mapped to this yellow triangle here. All of the green triangles over here get mapped to this green triangle here, and so on. And well, you could imagine, oh, first I should say that this also works in higher dimensions. So if n was 4, for example, we would have a 3-dimensional space V. And instead of having this hexagon, I'd have a little 3-dimensional polytope made out of 24 little tetrahedra. And those 24 tetrahedra correspond to the permutations of size 4. And you can tile the space V with these little polytopes, and then you end up getting this map to that polytope. But this is actually like a topological quotient map. So if you imagine here in this picture, like the centers of these hexagons form a lattice in this space V, well, really, we're just modding out by that lattice. So really, you should think of this hexagon as like a torus. It's a 2-dimensional torus. I can make that even more apparent by drawing these arrows that say we're gluing the opposite sides together. And so in general, we have an n-1 dimensional space V, and we end up getting this quotient map that goes to an n-1 dimensional torus. And that torus sort of corresponds in some way to the symmetric group Sn. Okay, so Lamb realized that you could take this affine Grassmannian reduced random walk, which is sort of walking along through the fundamental chamber here. And at each step in time, you just project down to the torus. So you're just keeping track of the color of the alcove that you're in. And this is a well-defined, what's called a lumping of Markov chains, or it's a well-defined projection of Markov chains. This is not obvious, but it's something you can check. And so that was his sort of key observation to realize that you get this well-defined Markov chain on the symmetric group. And this ends up being the same as this multi-species, totally asymmetric simple exclusion process. Now, actually, when Lamb wrote his paper, he wasn't aware that people had studied this thing before. He just said, oh, there's this interesting Markov chain. It seems to have a lot of really cool properties. But he didn't really know how to understand things like the stationary distribution. So for now, I want to try to put us into the mindset of Thomas Lamb when he was writing this paper and say, let's pretend we don't know that people have studied this thing before. Let's just say, okay, we have this Markov chain that we get by projecting to the symmetric group, and we don't really understand it. Okay, well, whatever this Markov chain is, it's not hard to show that it's irreducible, which implies that it has a unique stationary distribution, which I'll call zeta. So for now, zeta is just some mysterious probability distribution on the symmetric group that we don't understand. But whatever this is, we can use it to define this vector called psi lam. So Lam called this psi. I'm going to call it psi lam. And this is where we take the sum over all permutations W in Sn. So now I am thinking of Sn as a group of permutations. So I sum over permutations W such that W inverse of 1 is less than W inverse of n. And for each such permutation W, I take its probability in this stationary distribution that we don't understand, times this vector E sub W inverse of 1 minus E sub W inverse of n, where EI is just the ith standard basis vector in Rn. Okay. So notice first that this is actually in the space V. Remember, V is the set of points in Rn whose coordinates sum up to 0. Well, here I have a coordinate of 1 and a coordinate of -1, so they sum up to 0. So this whole thing is a linear combination of things in V, so it's also in V. And for now, we might not understand this, but what Lamb proved is that with probability 1, when you run the affine Grassmannian reduced random walk, you must travel asymptotically in the direction that this vector psi lam is pointing. Right? So this vector is pointing in some direction, and the affine Grassmannian reduced random walk has to go in that direction. And also, if you run the reduced random walk, that's the original version that's on the entire space V, not just the fundamental chamber. Well, in this case, you have to go asymptotically in the direction of one of the vectors in S in psi lam, where this is just the orbit of psi lam under the action of S in. So this is some set of n factorial different vectors. And here this is saying that when you do the reduced random walk, you have to go in one of those n factorial many directions. Okay. Well, so this is nice, but really we'd like to probably understand what is this vector. Like right now we have some kind of sum over permutations with some distribution. We don't really understand this. So we'd like to have a nice explicit formula for this. And actually Lamb conjectured a formula for this in his paper, and this was proven a couple years later by Arvin Iyer and Svante Linnaeus. So basically they came along and said, oh, you've rediscovered this thing called the multi-species TASEP, and people have studied this for a while, and they have these tools that they can use to compute the stationary distribution. And so then they applied those tools in order to prove this formula. So psi lam is just the sum over I less than j of j minus I times ei minus ej. So it's very simple. And in the case when n equals 3, this looks like this. So here I have this red dotted ray that's in the direction of this vector psi lam. And then the other red dotted rays are just the orbit of this ray under the action of S3. So Lamb's theorem is saying that you must go, when you run the reduced random walk, you must go asymptotically in one of these 6 directions. And you might think that this is kind of obvious by some sort of symmetry argument, like maybe, we're sort of just going down the middle, so it should be obvious that this is the direction. And it is obvious when n is 3, so this is kind of a misleading example, but when you go into higher dimensions, it's no longer obvious. So this is actually not easy at all. Okay, so I want to define a sort of billiardized version of this random walk that Lamb introduced. So to do this, I'm going to fix some probability p between 0 and 1. I'm going to just fix this probability throughout the talk. Now I'm going to start at some point in the interior of the fundamental alcove A, and I'll shine a beam of light in some direction. Let's say the initial direction is this vector eta. So eta is just the initial direction that I shine my beam of light. And now whenever the beam of light hits a hyperplane in the affine braid arrangement that it has not already crossed, it will pass through with probability p, and it will reflect with probability 1 minus p. Okay, but if it hits a hyperplane that it has already crossed, then it has to reflect. Just with probability 1, it has to reflect in that case. Okay, so here's an example. So let's say I start here. So this is for n equals 3. I start here at this point in the fundamental alcove, and I'm going to shine my beam of light in the due east direction here. So first, it's going to hit this line here. And when it hits this line, it will either pass through with probability p, or it will reflect with probability 1 minus p. Let's say in this example that it passes through. So I'll color this line pink, just like before, to represent that we've crossed through this line. Okay, well, now we hit this line here, and we'll either pass through with probability p or reflect with probability 1 minus p. Let's say we reflect. Okay, notice that this line does not become pink because we didn't cross through it. We just reflected off of it, but that's not the same as crossing through it. Okay, well, now we hit this line, and we either pass through with probability p or we reflect with probability 1 minus p. Let's say this time maybe we pass through. Now again, we either pass through or we reflect. Maybe this time we pass through. Now again, we either pass through or we reflect. Maybe this time we reflect. Okay, well, if we reflect, now we're facing this direction, and we hit this pink line. And when we hit a pink line, we have to reflect. So there's no other option. We have to reflect here. And then similarly, here we hit this pink line, and we have to reflect. Okay, and now we're going to hit this line again. We either pass through with probability p or we reflect with probability 1 minus p. Maybe this time we reflect again. Like that could happen. We could just kind of get stuck in here for a while. But now again, we have to reflect. And now again, we have to reflect. And now we either pass through or reflect. Maybe this time we pass through. And now maybe this time we reflect. Now maybe this time we pass through. Here we have to reflect because we hit a pink line. And so you can see we're sort of just going off, zigzagging along in this way. Okay. Okay, so this is what I'll call the reduced random billiard trajectory. And yeah, so this is a bigger picture that I drew for my paper. So here I have my green beam of light, and it's bouncing around in this zigzaggy pattern. And I have these 6 red dotted rays that are foreshadowing an analog of Lamb's theorem from before, saying that the beam of light has to go in the direction of one of these 6 red dotted rays. Okay. And I should say, when I generated this picture, I took p to be 3/4. So I have this fixed probability p that's determining the probability of passing through or reflecting. And in this example, p was 3/4. Okay. There's also an affine Grassmannian version of this. So again, affine Grassmannian for us just means fundamental chamber. And it's the same thing, except we're confined to stay in the fundamental chamber. In other words, if you hit one of the walls of the fundamental chamber, you have to reflect so that you stay inside of the fundamental chamber. And this is another picture from my paper. So I have my beam of light that's zigzagging along, and it's following this red dotted ray. Okay. Okay. So the theorem is, well, it's basically what I was just trying to illustrate. There is some vector, which I'll call psi eta p. So this depends on the fixed probability p, and it depends on eta, which was this initial direction that I chose to shine my beam of light at the beginning. So I have this vector psi eta p, and it has the property that with probability 1, when I run the affine Grassmannian reduced random Billiard trajectory, it must travel asymptotically in the direction that this vector is pointing. And also, if I run the reduced random Billiard trajectory, this must travel asymptotically in the direction of one of the vectors in the orbit of psi eta p under the action of Sn. Okay, so this is exactly what I was just illustrating with the red dotted rays for the case of n equals 3, but this is also true, for any n. Okay, so just like what Lamb did, we could write down a formula for this vector psi eta p. It's going to be some gross sum over permutations, except now there are even more terms that you have to deal with. And it involves this stationary distribution of some Markov chain that you get by projecting the affine Grassmannian reduced random walk to a torus. But a priori, we don't understand this distribution. And so it's just some gross sum that we don't really understand. So ideally, we would like to have a much simpler description of this vector psi eta p. In the same way that Arvin Iyer and Svante Linnaeus found this nice explicit formula for the vector psi lam, we'd like to do something similar for psi eta p. And I don't know how to do this in general for any eta and any p. But what I can do, and this is what I think is kind of surprising, is I can do this for any p for a particular choice of eta. So I want to assume now that my initial direction eta is this vector that I'll call delta. And delta is just, well, it's a bunch of ones followed by negative n plus 1. This is some vector in v, and I know it's in v because the sum of the coordinates is 0. So this is some vector. You don't really need to worry about how to visualize this, except I will say that in the n equals 3 case, so with these two-dimensional pictures, this is shining due east. So this is saying, shine in the eastward direction at the beginning. And I've been doing that in the pictures anyway, so sort of the same as what I've been showing. But if I assume that this is my initial direction delta, then there's this nice explicit formula for psi delta p. It's this sum over I less than j of some expression involving i's and j's and n's and p's times ei minus ej. Okay. Now, you might think this is kind of complicated, but it's really not. It's very explicit. You can write this down. You can compute it very concretely. It's much better than this gross sum over permutations that we don't really understand. So this is really the best, I think, that you could hope for here. I should say that this is up to a positive scalar multiple. I don't actually care about positive scalar multiples. I only care about the direction that my vector is pointing. So positive scalar multiples don't change that. But anyway, in most of the rest of the talk, I want to try to give some kind of a hint as to how I prove this. But first, let me mention that if you set p to be 0 here, then you recover the vector psi lam from before, up to a positive scalar multiple. Again, I don't care about positive scalar multiples. And, well, why is this? Well, remember, p is the probability that the beam of light passes through a hyperplane when it hits it if it hasn't already crossed through it. So if p is really close to 0, then most of the time you're going to be reflecting. You're going to be in some alcove, and you're going to reflect and reflect and reflect and reflect and reflect over and over again until eventually, once in a blue moon, you escape into an adjacent alcove. And then you're going to reflect and reflect and reflect and reflect and reflect over and over again until eventually, once in a blue moon, you escape into an adjacent alcove. And you're just going to keep doing this, very rarely escaping into a new alcove. And whenever you escape into an adjacent alcove, the direction that you escape into is going to be essentially uniform among the possible directions that you could have escaped into. So we basically recover Thomas Lamb's reduced random walk in the limit as p goes to 0 here. So if you'd like, you could think of the reduced random Billiard trajectory as like a Q analog of Lamb's reduced random walk, where Q is 1 minus p, so that if you set Q to be 1, that's like setting p to be 0 here. Okay. So just as before, I want to project from my affine Grassmannian reduced random Billiard trajectory to a torus so that I'll get some finite state Markov chain. Except now, instead of having a Markov chain where the state space is just Sn, now the state space is going to be Sn crossed with Z mod in Z. And the reason is, well, imagine I have my affine Grassmannian reduced random billiard trajectory, which is some beam of light that's sort of bouncing around in the fundamental chamber here. And at each point in time, I project down to the torus. So I get this projected beam of light that's sort of bouncing around in the torus in some random way. Well, at each point in time, I want to keep track of where in the torus is my beam of light. So that's encoded by an element of Sn, which is telling me which little toric alcove contains the beam of light at that point in time. But I also have to keep track of the direction that the beam of light is facing. And it turns out that there are only n possible directions that the beam of light can face at any time. So the direction can be encoded by an element of Z mod in Z. So overall, a state in this finite state Markov chain is encoding where in the torus is the beam of light and which direction is it facing. Okay, well, I actually want to be more explicit about what this Markov chain is. It's going to be some kind of a variant of the multi-species taste-up on a cycle, which I was mentioning before. But before I tell you about this Markov chain, I should probably tell you about the multi-species taste-up on a cycle, because I haven't defined that yet. Well, actually, I'm going to define something even more general called the multi-species ASEP. So there are kind of a lot of acronyms in this area, and you sort of just have to get used to it. But anyway, we're going to fix some parameter t between 0 and 1. So t could be 0, but let's assume it's not 1. And lambda is going to be some weakly decreasing tuple of n non-negative integers. Okay, so this is my lambda. And here, this is just some notation. So if I have integers k and k prime, I'll say f sub t of k prime is 1 if k is bigger than k prime. I'll say it's t if k is less than k prime. And I'll say it's 0 if they're equal. So there's nothing complicated here. This is just notation. And now S lambda is going to be the set of permutations of lambda. In other words, these are just the tuples that I can get by rearranging the parts of lambda. And of course, if lambda is just n minus 1, n minus 2, dot, 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 1, well, then S lambda is really just the same as the symmetric group Sn. And this is actually the case that I care about the most. This is the case that occurs when you project lamb's affine Grassmannian reduced random walk to the torus, and also when you project the affine Grassmannian reduced random billiard trajectory to the torus, you end up getting this choice of lambda. But we might as well work with arbitrary choices of lambda because there's no harm in working more generally. Okay, so what is the multi-species ASEP? Well, it's a continuous time Markov chain where the state space is S lambda. So a state is just some tuple that I get by rearranging parts of lambda. And so let's say I have this tuple mu. So let's say it's mu1 through mu n. I can represent this tuple by placing particles of species mu1 through mu n along a cycle. So the species is just like the type of particle, basically. So here I have these particles of species 5, 6, 1, 1, 3, and 3. And so this is representing the tuple 5, 6, 1, 1, 3, 3. Okay. And well, what are the dynamics here? Basically, adjacent particles can swap places with each other at certain rates. So if I have two particles that are adjacent to each other on the cycle, if the one on the left is smaller than the one on the right, then they will swap with rate t. And if the one on the left is bigger than the one on the right, then they swap with rate 1. So here, the 3 is less than the 5, so they swap with rate t. 5 is less than 6, so they swap with rate t. 6 is bigger than 1, so they swap with rate 1. 1 is less than 3, so they swap with rate t. The 1s don't swap. I mean, even if they did swap, it wouldn't make any difference because they're the same. Same with the 3s here. So this is how the Markov chain works. So this is the multi-species ASEP. There's been a huge amount of literature devoted to this. There are tons of papers about this and other variants of this with connections to physics and various other things. So I'm only going to give you a very small sliver of the literature about the multi-species ASEP. I'm just going to mention a few things that are known about the stationary distribution. Well, first, let me mention that this multi-species TASEP, which I mentioned earlier, this is what you get by projecting the affine Grassmannian reduced random walk to the torus. This is the special case where t is 0. So if I want to understand that affine Grassmannian reduced random walk, it suffices to understand the t equals 0 case. But we could also work with, arbitrary t as well. So Ferrari and Martin introduced these objects called multi-line queues, which are some combinatorial objects that you can use to describe the stationary distribution of the multi-species T-set. So this is specifically in the case when T is 0. But then this was generalized by Martin, who showed that actually you could use these objects to compute the stationary distribution for any T. So this is for the multi-species A set. Okay, so this is what a multi-line queue looks like. I'm not actually going to define these, but basically it's something that looks like this. You've got a bunch of balls arranged on a cylinder, connected by some pieces of string according to some rules. So if you've ever seen Olja Mandelstam give a talk, you've probably seen these things before because she's done a lot of really interesting work with these objects. Actually, I think she gave a talk in the Cascade Lectures maybe a couple of years ago. I don't know if these were there, but I assume they were because I read the abstract and it seems like it was probably involving these. But anyway, we have these objects. And there's this paper by Sylvie Corteil and Olja Mandelstam and Lauren Williams. And this was building off of previous work of Cantini, De Geer, and Wheeler. And they define these things called A-set polynomials, which look something like this. There's kind of a lot going on here, so let me try to unpack this. Here, Q and T are just some parameters. T is the same parameter that I was using to define the multi-species A-set from before. And Q is just some other, let's say, real parameter. And x1 through xn are some variables. And mu is a state of the multi-species A-set. So it's an element of S lambda. And now f mu is just some polynomial indexed by the state mu. It's a polynomial in the variables x1 through xn, and its coefficients are some rational functions in Q and T. So I won't actually define these, but there's some particular polynomials that you can write down in a very clever way. And they're interesting for a couple reasons. One is that they're closely related to Macdonald polynomials. So if you sum these up over all of the states in S lambda, so you just take like sum over mu in S lambda of this thing, you end up getting the Macdonald polynomial indexed by lambda. But then also, these tell you about the stationary distribution of the multi-species A set. If you set Q to be 1 and you set all the X's to be 1, then this is the stationary probability of the state mu in the multi-species A set up to a normalization factor. We don't have to care about the normalization. That's just to make sure that it's actually a probability distribution, but let's not worry about that. But basically, this is saying that these are encoding the stationary distribution if you set Q to be 1 and you set the X's to be 1. Okay. Okay, so I want to define a variant of the multi-species A-set that I'll call the stoned multi-species A-set. So here, the state space is going to be S lambda cross with Z mod NZ. And to represent a state mu comma J, well, I'm going to represent mu just like before. Right, so mu is some tuple, mu1 through mu n. So I put particles of species mu1 through mu n along the cycle, just like before. But now to represent J, I'm going to put a pink stone on site J, and I'm going to put a green stone on each of the other sites. Okay. So actually, in a previous version of this talk, I had a gold stone instead of a pink stone, but I saw Wicked last week, and so now I think pink goes good with green. So now I'm using pink. But anyway, this is what a state looks like. And so I have this tuple here. The tuple is 2, 1, 3. Okay, and so that's my mu. And I have this pink stone sitting on site 2, so here J is 2. Okay. Or if I looked at this example, mu is 3, 1, 2, and the pink stone is on site 1, so here J is 1. Okay, so I'll explain the hexagons in a second, but let me first talk about the dynamics of this. It's a little bit complicated, so just, I guess, try to bear with me. So basically, this is a discrete time Markov chain. And at each point in time, the pink stone is going to move one space clockwise. So that will always happen for every transition. The pink stone always just moves one space clockwise. So it's going to swap with one of the green stones. And when it does this, so let's say we're transitioning from state mu comma J to some new state. So the pink stone moves from site J to site J plus 1. It's going to send a signal to the particles that are sitting on sites J and J plus 1, telling them to swap places. But the signal might not reach the particles. So the probability that the signal actually reaches the particles is this probability P that we had from before. So with probability 1 minus P, the signal doesn't even reach the particles, in which case they don't swap because they didn't get the signal. But even if they do get the signal, they can choose to ignore it. They can say, actually, no, we don't want to move. We're fine where we are. We're just going to stay still. So if the particles receive the signal, then the probability that they actually follow their orders and do the swap is this f sub t of mu j plus 1 that I have from before. So remember, this is 1 if mu j is bigger than mu j plus 1. It's t if mu j is smaller than mu j plus 1. And it's 0 if they're equal. Okay. So as an example, if I look at the transition from this state here to this state here, this happens with probability p times t. And the reason is that, well, you can see the pink stone moved. That always happens in every transition. But you can see that the 1 and the 2, these particles, they swap places with each other. So what happened is the signal actually reached the particles. That happened with probability p. And then once the signal reached the particles, they actually followed their orders, which happened with probability t. And it's t because 1 is less than 2. So overall, the probability of this transition actually occurring is p times t. Okay, and then there are similar computations for these other arrows here. Okay, well, let me explain these hexagons. So basically, the stone multi-species ASEP, in the case when you have particles of all distinct species, so let's say 1 through n, this is actually modeling a random combinatorial billiard trajectory in a torus, where basically if two particles do not swap places with each other, then that corresponds to the beam of light reflecting off of a little toric hyperplane. And if they do swap places with each other, that corresponds to the beam of light passing into an adjacent alcove. So here, the beam of light reflects, and then it passes into this adjacent alcove, and then here it reflects, and then here it passes into an adjacent alcove, but this is a torus, so it had to wrap around like this, and then it reflects again here. So the stone multi-species ASEP is encoding this random combinatorial billiard trajectory in some way. So actually, a few days ago, I found this AI thing by Google called Illuminate, where you can upload a paper and it will create a dialogue between two bots that basically talk about the paper. So I uploaded this paper to Illuminate and got these bots to discuss it for like 4 minutes. And I don't think in the paper I mentioned that there's a connection between these interacting particle systems and physics. Maybe I say that, but like somehow it figured this out and it was talking about how there's a connection with physics. And at some point, one of the bots said, wait, so you're saying that there's a connection between bouncing light and physics? I thought that was pretty funny. But anyway, yeah, so I think Illuminate's pretty cool, but yeah, I thought that was kind of funny. Okay, so, well, the theorem is I can compute the stationary distribution of this stone multi-species ASEP. So if I want to compute the stationary probability of mu comma j, I take this ASEP polynomial f mu from before. And just like before, I plug in q equals 1, and I set all the variables to be 1, except for the variable xj, which I set to be this number chi, which is this 1 minus p over 1 minus pt. Okay, so it's very similar to what you do for the multi-species ASEP, except now you have this extra number that you plug in for the variable j. Okay, or the jth variable. And in the case when t is 0, this is what allows me to get this formula for the vector psi delta p from before. Because this, in the case when t is 0, this stone multi-species ASEP is really what I get by projecting the affine Grassmannian reduced random billiard trajectory to the torus. So I can understand that by understanding this stationary distribution here. Except I also have to analyze these multi-line Qs. So I didn't define these, but basically there's some analysis that you have to do with these multi-line Qs. And it's not obvious that this should work. Like when I first started doing this, I thought like there's no reason why this should give something nice, but somehow there's like this magical property of these multi-line Qs that actually allows things to work out very nicely. So I end up getting a nice exact formula for psi delta p, which is this expression that I had from before, where it was like the sum over I less than j of some expression involving i's and j's and n's and p's times ei minus ej. So I get that using this and also using the multi-line Qs. Okay. Okay. Well, so actually there's a more general version of the stone multi-species ASEP. And in this more general version, we can number the green stones from 1 to n minus 1. And now the only difference is that instead of having one fixed probability p, we have probabilities p sub I. So say p1 through pn minus 1, and we associate the probability pi with the green stone numbered I. And now the only difference is that when the pink stone swaps with a green stone, numbered I, and sends a signal to the particles telling them to swap places, now the probability of the signal reaching the particles is this piece of I. So the only difference is that now the probability of the signal reaching the particles depends on which one of the green stones was involved in the swap. Okay. And in this more general setting, I can also compute the stationary distribution of the stone multi-species ASEP. And it's again by using these ASEP polynomials, but now instead of plugging in one number chi and a bunch of ones, now I have numbers chi1 through chi(n), and I plug them in some permuted order according to some rule. But you can compute this now. And so if you imagine choosing these PIs as just like some generic probabilities, this is saying that you can get the stationary distribution of the stone multi-species ASEP by plugging in some generic values into these ASEP polynomials. So I went to a seminar dinner back in April, and I asked Lauren, like, have you seen something like this? Have you seen some Markov chain where you get the stationary distribution by plugging in generic values into your ASEP polynomials instead of plugging in all ones? And she said, oh, actually, yes, I just wrote a paper like last week with Arvin Iyer and James Martin. And I guess they had posted this on the archive just a week before, and somehow I missed it. And basically, the goal of this paper is to do exactly this. So they construct some Markov chain where the stationary distribution is obtained by plugging in generic values into these ASEP polynomials. Okay, but their Markov chain is actually totally different from mine. So it's some completely different thing. So in some sense, I was sort of answering the same question that they were answering, although I was kind of led to this from this billiards perspective and sort of stumbled upon this by accident. But they have their Markov chain, which they call the inhomogeneous T-push TASEP. So there are kind of a lot of acronyms in this area. You sort of just have to get used to it. But yeah, so it's some Markov chain that has this property. Okay. So I have to say, I kind of have a bias toward my own Markov chain here. And the reason is that there are other variants of the multi-species ASEP. And you can try to play the same game with these other variants. So basically, there are some variants where you have some polynomials and you can get the stationary distribution by plugging in particular specializations. And you can say, can we cook up some Markov chain where now the stationary distribution is given by plugging in generic values into those polynomials, just like we did here. And I think they tried to adapt their inhomogeneous T-push TASEP to these other settings, and they didn't really see how to get it to work. But with the stoned approach, it actually works without too much difficulty. So I'll just very briefly mention a couple of these variants. So one of them is called the inhomogeneous TASEP. This is introduced by Thomas Lamb and Lauren Williams. It's been studied further by many others. So one reason people care about these is that the stationary distribution is conjecturally related to Schubert polynomials in a really interesting way. This is still open, although it's been resolved in some special cases. So particularly Kim and Williams have a paper where they settle this in some cases, but it's open in general. But then also there are these polynomials called inhomogeneous TASEP polynomials. These were introduced by Cantini. And you can get the stationary distribution of the inhomogeneous TASEP by plugging in some particular specialization into these polynomials. And so I define this thing called the stoned inhomogeneous TASEP, and you get the stationary distribution of this Markov chain by plugging in generic values into these inhomogeneous TASEP polynomials. Okay. And this also has a billiards interpretation. So I was mentioning a few slides ago that the stoned multi-species ASEP has an interpretation in terms of like a random combinatorial billiard trajectory in the torus. This also has a similar interpretation. It's just a bit more complicated. Okay, there's also this thing called the open boundary ASEP. This was introduced by Spitzer back in the 1970s. And here, the stationary distribution is obtained by taking these things called open boundary ASEP polynomials and plugging in particular specializations. And these open boundary ASEP polynomials are very closely related to what are called Kornwinder polynomials. So the Kornwinder polynomials are basically like type C analogs of Macdonald polynomials. And in the same way that you can add up the ASEP polynomials to get Macdonald polynomials, you can similarly add up the open boundary ASEP polynomials to get these Kornwinder polynomials. And so again, I defined a stoned version of the open boundary ASEP, and I showed that you get the stationary distribution by plugging in generic values instead of this particular specialization. And this also has a Billiards interpretation, except now instead of projecting from the affine symmetric group to a torus, we project from an affine Weyl group of type C to a torus. So it's sort of like a type C version of the Billiard stuff that I was talking about earlier. Maybe I should mention, in case there are people who are familiar with this, that when you define this open boundary ASEP, there are these 4 boundary parameters that you need. So they're alpha, beta, gamma, and delta. And in order to get this to work, I have to assume that alpha equals gamma and beta equals delta. So I guess it's still open to try to do this in full generality for arbitrary alpha, beta, gamma, delta. But still, I think it's nice that I can do this even with the assumption that alpha equals gamma and beta equals delta. If you don't know what I'm talking about, that's fine. Okay. So the last thing I want to mention in the last few minutes is essentially an open problem. And the idea is that, well, you can kind of do this process of stoning some interacting particle system, I think, in a much more general sense. So you have some kind of interacting particle system, and you could say, let's place a stone somewhere and have it kind of walk along and send signals to the particles, and the signal reaches the particle with some probability. And if the signal reaches the particle, it can choose whether to ignore it or not. So it's sort of like what we were doing with the stone multi-species ASEP. So I want to define essentially a stoned version of what's called the ASEP on Z. So this is like the ASEP on the integer lattice. And so the ASEP on Z is a very well-studied process. So it was originally studied in a special case by Johansen in a very revolutionary work. And then later it was studied by Tracy and Whittam in another very revolutionary work. So I'm sort of defining this stoned version of this ASEP on Z, which I'm going to call the scan ASEP. Okay, so the idea is, well, we have some configuration of particles sitting on the integer lattice. And I want to assume that all of the sites sufficiently far to the left are occupied, and all of the sites sufficiently far to the right are vacant. Right, so that's what this is representing. All the sites over here to the left are occupied. All the sites over here to the right are vacant. And now I'm going to place a stone somewhere here, let's say to the left of all of the vacant sites. And I'm going to place it between 2 sites. So I'm putting it here. And now the stone is just going to march along one step at a time, going to the right. It's just going to go over to the right, one step at a time. And whenever the stone is between 2 particles, it doesn't do anything. And whenever the stone is between 2 vacant sites, it doesn't do anything. But if it's between a particle and a vacant site, where the particle is on the left and the vacant site is on the right, then the particle will move into that vacant site with probability P. So I have this probability P from before, and so that's the probability of this particle moving into this site. So in this example, let's assume that maybe the particle does not move in this case, but the stone still moves over. And now the other case is if the stone is between a vacant site and a particle, where the vacant site is on the left and the particle is on the right, then in this case, the particle moves over with probability P times T. So I also have this parameter T from before. So I have this P and T, and the point is basically a particle will move right with probability P when the stone is telling it to, and it will move left with probability P times T when the stone is telling it to. So in this example, let's assume that maybe this particle does move. Okay, so now the stone moved again. And now we have the same situation where the particle moves with probability P times T. And let's say in this example that it does not move. And now this one moves with probability P. Let's say it does move. And now nothing happens because it's between 2 particles. Now this moves with probability P. Let's say it does not move. Now this moves with probability P times T. Let's say it does move. And so now the stone is further to the right than all of the particles. So it's not going to do anything from now on. So this completes one, what I'll call scan. So a scan is basically, you take the stone, you put it over here to the left, you let it march along doing this until it gets further to the right than all the particles. So that's one scan. And after you've completed one scan, you take the stone and you just move it back and you do another scan. So now the stone is sitting here again between these particles. It does nothing. And so now it's going to move over. This particle moves with probability P. Let's say in this example, it does move. Now, again, this is going to move with probability P. Let's say it does move. And now nothing happens. Now nothing happens. Now nothing happens. Now the particle moves with probability P. Let's say it doesn't move. And so that completes another scan. And you just keep doing this over and over. You just do scan after scan after scan. And what we want to know is, how do the particles get arranged over a long period of time? How do they configure themselves? So we can think about one of these configurations of particles using a Young diagram. So basically, it's this rotated Young diagram in Russian notation. And whenever I have a particle that corresponds to, oh, oops, what did I do? Whenever I have a particle, that corresponds to a down step, which I've drawn in red. And whenever I have a vacant site, that corresponds to an up step, which I've drawn in green. So here I have a bunch of down steps followed by up, down, down, up, down, up, down, and then a bunch of up steps. And so we can try to understand, as we run the scan ASEP, how does this partition associated to the configuration of particles, how does this change? Like, what does it look like? So building off of this work of Johansson, I showed that if t is 0, so here I have to assume t is 0. In this case, when you run the scan ASEP, you can look at these associated partitions, and if you scale them appropriately, they will converge to a certain limit shape, which I can write down explicitly. So the point is, there's some limiting shape that you get for these partitions if you scale them appropriately. But this is specifically when t is 0. And I should say that Johansson's particle process is the version of the ASEP on Z where t is 0. But then, as I was mentioning before, there's a more general version for any P and T. This is like the ASEP on Z, which was studied by Tracy and Whittam. And so the scan ASEP in general is a stoned version of that. And I don't know how to understand the limiting behavior of this. So I think it would be really interesting to understand the limiting behavior of the scan ASEP for arbitrary T and arbitrary P. This would be like a stoned analog of this revolutionary work of Tracy and Whittam. Okay, well, I think that is all that I have to say. So thank you, everyone, for coming. And yeah.
Thank you. It's very nice. Are there questions?
I have a question.
Yes.
Hi, Colin. Could you
Hi, Grace.
could you like go way back to where you were doing your red dotted lines?
Yes. Okay, it takes a while because there are like
Oh yeah.
some high res photos or something, but okay, I'm trying.
I was wondering, I think you sort of said this, but I didn't quite like hear the answer if you did. So you have your psi, and then there's also Lamb's psi. And I was wondering, like, how does yours, you said as p goes to 0, it goes towards psi lamb. Do you know what happens like as p goes to 1, or like just do you know anything about how it moves? Like, is there some range that it like moves in or something?
Yeah, so well, okay, for the two-dimensional picture,
Mhm.
as p goes to 1, it's going to approach like a horizontal line, basically. It's going to approach
Mhm.
like this direction here. So these two rays will sort of close in on, like, get closer to each other. In higher dimensions, something similar should happen, where like at p equals 1, it should be like very close to this initial direction delta. And if p is very close to 0, then it's very close to psi lamb. I don't understand though, like, what is the curve? Okay, okay, I don't understand the curve that it traces out. Like in here, it's easy because it's like there's only 2 dimensions.
Yeah.
But in general, it could like do some crazy thing. I don't understand that. And I don't really understand a lot about this for other okay, sorry. I was answering the wrong question. Okay. Sorry, there are two things, eta and p. If you're varying p, okay, yes. So if you vary p, there's some curve, and this follows from the formula that I wrote down. I don't know exactly what it looks like, but like this is some formula and you can write it down, right? So you get some curve that it's tracing out. I guess what I was just answering is that I don't know how to understand the case where you vary eta.
Even if you keep p fixed.
Yeah, right. Even if you keep p fixed. But yeah, yeah, if p is close to 1, then the vector should be very close to this psi lamb. Or this is not psi lamb. That's if p is 0.
Like your hyperplane.
Yeah, the vector delta, I mean.
Cool. Okay, thank you.
Yep.
So do these statements about this limiting behavior translate to statements about if you take longer and longer reduced expressions in the affine Coxeter group, that something about like the expected ratio of the number of simple reflections.
Right. So I guess, yeah, how do you, so you'd want to think about, I guess it's approaching something like some limit point on the boundary of the Tietz cone, basically. And you could describe that limit point as sort of like an infinite reduced word in some way, like because you're sort of like a limiting point would be described by which hyperplane separate it from the fundamental alcove. So in some sense, it's saying something like that. Yeah.
Yeah. Hmm. Other questions?
I had one question about near the end when you mentioned the known situation when p goes to 0.
Yeah.
I was thinking that so in that case you're going to get more and more things going to the right and never going to the left, right?
Yes.
So I was imagining um that the diagram would keep getting bigger and bigger over time. Is that the wrong way to think
Yes.
about it?
No. So the associated. Yeah. So this Young diagram will get bigger and bigger, but you scale it according to
I
some
see.
factor,
Okay.
so that yeah, when you scale it, it approaches some limit shape.
That makes sense.
Any more questions?
Yeah, so Colin, in that, how do you expect it to differ from the situation where there's no stone, but you just fire vertices at random and a vertex
So, like this one.
with usual rules?
I mean, I don't know. Like, okay, I guess intuitively, I might expect it to be something like here, the limiting shape is sort of just stretching the x coordinate by some factor of like 1 minus p here. Like if I got rid of if p was 0 here, this would basically be just Johansson's result. So I kind of expect maybe something like that where you scale by some 1 minus p, except like I looked at the way that Tracy and Whittam actually do this, and I couldn't see like how to modify this in an appropriate way. And it wasn't clear to me. Like they're doing a bunch of like solving equations and setting up a bunch of complicated systems, and I didn't really see how to do something like that in this setting. But there's sort of like a nice trick that you can do when t is 0 that will reduce this to Johansson's case. So I'm really building very heavily off of his work using this nice trick. I don't have that nice trick if t is not 0.
Oh, I see. Okay. I did have one comment about early on. I like your discrete billiards, but I wouldn't want to contrast it with what you call mathematical billiards. I think we've established now that discrete mathematics is part of mathematics, and
Okay.
maybe instead just call the old one continuous billiards.
Okay, yeah, actually that's a good point. Yeah, I like that better. Yeah. Yeah, continuous billiards. Okay.
Any other questions or comments or there's also a chance to chat during the coffee break. Let's thank Colin again.